Bismillahirrahmanirrahim. Assalamu alaikum. This is Dr. ADNAN, your course teacher for a course CE201 Engineering Surveying, and this is obviously a fall 20. In this course, what we are going to study, or let me put it in this way, is that this is a course code having a title CE201. I forget to correct this. And this is a 3 theory and 1 practical hour course. That means 3 lecture hours and 1 practical hour each week. And then these are the course content. The first one is surveying, drafting, and computations. The highway and railway curves, construction surveys, hydrographic surveys, control surveys, globally positioned system, and photogrammetry. This course will be shared course with me. Dr. Asher will be teaching you. So I will be teaching you only these two parts, surveying, drafting, and computation, and highway and railway curves. And I will be taking 1 lecture per week. So this is how I intend to complete this course. Um, since this is an online course, again we have 10 lecture weeks of theories, and then the rest will be for the practicals. So I will have 10 lectures. I have a class uh, on every Tuesday between 9:30 and 10, between 9:30 to 10:20, and these are the course topics. Uh, for you, this November 3 is important, that there will be a quiz, and we will have a midterm, tentatively maybe in the 9th week, and then and at the 10th lecture, along with this topic, there will be another quiz too. So this is, in summary, I will be taking 2 quizzes uh, that will have 7.5% marks each, and then there will be a midterm that will constitute 20% marks, and then there will be assignment, and there will be 2 assignment. Uh, this will be taken on 4th and 9th week of this semester. This is the book Elementary Surveying, an Introduction to Geomatics. The latest edition is 15th by Charles T. Gilani. And then there is a reference book by Barry H. Kavanagh. I presume that since you already have taken this course, Surveying 1, so you may have either of these 2 books. There is a soft copy that is also available of the 13th edition, and that I will share with you in the classroom, and you can get the 13th edition. But for me, I always like students to buy a hard book, um, and that may not be very costly, maybe 300 rupees like that. So I recommend this to be bought, but if you don't prefer not to, then you always use this soft copy, and that is available on the classroom. Now, as you know, that we have accredited with outcome-based education system. So, for having accredited outcome-based system, you must know what are the course learning objective of each of the subject that is being taught. So, this course has got 3 objectives. One, enable the students to understand advanced concepts of geospatial positioning and its analysis for determining position of the point. This comes under C3 of the cognitive learning level. Actually, this portion will be covered by Dr. Asher. And then the second CLO enable the students to calculate areas and volumes from topographic maps and understand highways and railroad curves. This is a C2 course, and this is the part that I will be teaching you during this session. Last but not least, uh, you will be have you will learn to use digital equipment in the field of surveying. That's it, SS3. And actually, this is the third part again. Uh, this will be actually taken by Dr. Asha. Now, how this related to your overall program learning objective and what are the assessment? Now, when we say geospatial position, this is taxonomy level 3, C3, and that pertains to engineering knowledge. And obviously, both the quizzes and the assignment, midterm and final exam, they will taken care. And so is the second objective. This is C2, and in which you will be doing a lot of problems. That is what I will call the problem analysis. It doesn't mean that you will be not be using doing problems in the first CLO. You will be, but this the level of that problems will be just uh, comes under this category of engineering knowledge. And then the last but not least, you will have a lab, and this will be called a modern tool usage, and this will be taken as lab quiz, Viva, lab work. And not only that, you will be using a software, you will be learning a software for solving the problems, and that will also comes under this category of C3, S3. Now, when we talk about this, the first chapter that I'll be discussing, and if you have a soft copy with you, chapter 12 and chapter 26 is the area. This particular topic that I'll be teaching in couple of weeks to you will be held. And then I always have the tutorial sheets, and you can say this is an assignment sheet, and that we will solve time and again to learn those problems. Now let's start formally with a topic that is a topographic surveying. Now the word topo means land and graph means the mapping. So what I mean here is you will learn the techniques of surveying that will help to you to draw the topographic map of the areas, and not only to draw but to understand the topographic area of a topographic map of any area. And once you know the map, and you will apply this knowledge to calculate the areas and volumes. As I can say, maybe this topic, I'm covering this topic only on the context of calculations of volumes and areas. The second part, or the second section of this course that will be taught by Dr. Asher will actually give you idea how to draw those maps. So what is a topographic survey? Topographic surveys are used to record the information necessary to draw a topographic map. Now, topo maps are a two-dimensional representation of three-dimensional object. Now, as you can see from this picture, it shows only the XY, but it is not three-dimensional. But the third dimension is shown in the form of those contours, or we call the elevation. So even though this is a two-dimensional map for an ordinary profession, but for an engineer, this is a 3D map. And what is the task? Is to determine the relief of the Earth surface and locate critical points on it. What I mean by relief is the high and low points on the Earth surface, and try to locate those points accurately on the map. And when we say topographic maps are not only does not only record elevation, but they also include the important surface features. These are slope, hills, streams, lakes, trees, soil type, man-made objects, and etc. So in summary, you can say topographic maps contains all the natural and man-made features existing on the surface of the earth. For man-made, we means buildings, the water structures like dams, utilities like gas lines, telephone lines, electricity poles, the roads, obviously, the railway lines, and the airports and all other things that comes under uh, that's not created naturally by the nature, but by the man himself. Now, it's it's not necessary that all features should be included on the maps, but according to the purpose it is shown. But let me remind you, in today's world, what you do, you draw all the features that is highlighted here in a topographic map. And if you know AutoCAD is the software version of the drawings, there are different layers on which each of this structure will be defined, and what you do is, for viewing the particular structure, there you can only see the software will is good enough to show you the features you would like and hide other features that you don't want to have interest at that particular of time. So yes, though I say it's a features should be included on the maps, but maps are drawn once in a life. So when you go to the site, we try to capture every feature as we can, and obviously by using AutoCAD drawing, we can hide those features when presenting for the specific purpose we intend to use those maps. Obviously, when we say map, it is drawn at a scale, and the scale is defined as the relationship between the distance on the map and the distance on the ground. It is usually expressed as a fraction or a ratio. Uh, Normally, 1 is to 10,000. What I mean by 10,000 is to 1 that 1 unit on paper represent 10,000 unit of the ground. But don't be confused with the ratio. No, what I mean is that if I say this this is a ratio, there can be any unit. So Is it like this 1 kilometer on the paper will be shown as 10,000 kilometer on the ground? What do you think? If as a mathematician, you say, yes, sir, why not? But it isn't true. You cannot have a paper of size in which you draw 1 kilometer. So logically, even though the units are not mentioned here, but the unit, the paper unit, that is one, it should be maybe 1 centimeter, 1 inch, or 1 millimeter, not more than that. And then when we say 1 millimeter, I mean 10,000 millimeter on the ground. And when we say 1 centimeter, I mean 10,000 centimeter on the ground. And I will say 1 inch, it means 10,000 inch on the ground. So yes, don't get confused with this ratio, because the paper is not big enough to draw say 1 meter, and you can use for for drawing 1 meter on that scale. You have to use a 1 meter paper, even though you have a 1 meter paper, but then every information could not be gathered on one paper. So be logical. Be logical. So 1 centimeter, 1 to 10,000 means maybe 1 centimeter, maybe 1 millimeter, or 1 inches, representing the same equivalent unit on the ground, right? Now, to continue with this, the first number always represent the map and the second number on the ground. Now, when we say the larger the second number, the smaller the scale of the map. For example, a map of an area 100 miles by 100 miles drawn at a scale of 1:63,660 would be 8 feet square. If the same area was drawn with a scale of 1:316,800, it means 1 inch is equal to 5 miles. The map would be less than 2 feet by 2 feet. So the bottom line is, the larger the denominator, the smaller is the scale of the. Well, this is very logical. Divide 1 by 10,000 and 1 by 100,000, which is smaller. That's very obvious. Now, and also the scale of the map is determined by the size of the area and the desired detail. If the area is large, it is a common practice to use one map with a large scale to show the entire area, and other map with the lower scale to show the certain features of the other areas. Now, generally, the companies and the government agencies uh, use map like United States Geological Survey and Forest Service Company. They use a common scale of 1:24,000. So with each scale, each map represents 7.5 minutes of latitude and 7.5 minutes of longitude. And these maps are called 7.5-minute quadrangles. Now, every map has symbols, and symbols are used for many features on a map to reduce the amount of the word. Now, there are several standards that have been adopted, like you see that this a rock is shown by this shape, the mathematic features, submerged areas, the railroads, everything has its own symbol, and that symbols are like building has a rectangular symbol. The school and churches, they have a special design, and mosques, they have a different task and different domination, and generally they are what I say is universal. Like the 12 highway, there is a light duty road, There is an unimproved road, there's highway, there's the pipelines, telephone lines. So each have its all this. So if you're interested, you can copy this site, and obviously this PowerPoint will be also shared with you. So just all you need to do is to copy this, and you can see those standard symbols. Uh, Topographic maps are not usually considered to be extremely accurate. The pyramid function is for planning purpose. It is not intended to show every small depression or hill. Most measurements can be taken within areas accuracy less than the least count of the instrument. Uh, for, for instance, elevations are taken as 0.1 foot. So there should be 2.004 feet, but we'll take this as 0.1 feet. So when we show elevation, it will be 2.1, 2.3, 5.7, 5.8, but not by 5.9999 feet, right? It's not like this. Similarly, the distances, they are taken as nearest to 0.1 feet. So horizontal angles we take is near degree, no use of taking 2 degree, 15 minutes, 30 seconds, just take it as 2 degree. And when the vertical angles, take the least count of whatever the instrument has. So what are the sources of error? It can be an instrumental errors. The instrument may not be very well calibrated. Maybe someone has not used the readings accurately. Maybe there is inadequate control points. Maybe the instrument cannot reach beyond its limited sight distance. The distance is too far away. What I mean is you have to shift the instrument in this case. Yes. For instance, you are standing in the valley and you try taking the want to take the elevation of the of the mountain that is too high. So that's may not be a very good station. Maybe somewhere between there, or maybe top of the hill. That will be a good idea. So maybe sometimes uh, the error may be, we did not use the correct equipment. Maybe the instruments were not level or not set according to its requirement. And then there will be a two meaning of it. So there is a distance between error and the mistakes. Mistakes can be rectified as well. There are errors that is under control, and there are errors that is beyond our control. So we can only correct the errors that is within our controls. And obviously this is a mistake. For example, there was a lake and you failed to map that lake in the maps. This is a mistake, and the mistake has to be redone. Errors can be corrected. Now, one of the major feature, that's why we call this as topographic map, is the contour lines. So what is contour lines? Contour lines are lines of constant elevation. They show you major topographic features like stream beds, hilltops, ridge lines, edge or cliffs, and shoreline, etc. The edge, center line, intersection of roads, the beginning or ending point of the bridges, culverts, and other point road structures, and all known sociographic features, city limits, county lines, housing district boundary lines. Remember, what we are discussing here is what is included in the topographic map. The contours, and obviously these features like the city limits, bridges, roads, like that. We also includes, as I've said in the introduction, the utility lines like overhead electricals, sewers, storm drains. Then there is spot elevations, any additional features which will enhance the reader's ability to read and use the map for its intended purpose. So let's start formally our discussion on the contour lines. Contour lines, as we call the line of same elevation, are a line that joins those elevations. But there are different characteristics. They are very continuous. They are parallel until or unless that two undish that a series of V shapes indicates a valley and the V point at higher elevation. U shapes indicates a ridge. The U shape will point to lower shape. So if you find a V shape, it means you're talking about the valley. And if you see the shape of contours in U, it's a ridge. And you know what is ridge? Huh? I don't need to explain to you. And if you don't, just remember the highest point, the pointing, the top point of the mountains is a ridge. Evenly spaced line indicates, so if the contour lines are equal, then there's a uniform slope. Now, if the contours are very close each other and they have increased elevation, it is indicating a hill. And series of close contours with decreasing the elevations indicates a depression. So if your elevation is increasing from say from the left to from outside to inside, it's a hill. And I will show you the map as well. So don't get worried and do not think what I mean by increasing elevation and what I mean by decreased elevation. Will it be outside, inside, or inside or outside? This will be shown to you in a while. But you know, since I was discussing contour line, so I say contour with decreasing elevation indicates a depression. So what if you know the characteristics of the contour? So whenever there is a map, topographic map uh, presented in front of you, you have an idea of the area of the slope uh, and the terrain conditions in front of you by just knowing these conceptual points. So now when say close contours may be identified with a positive hill or negative depression. Close contours may include Hachure marks. Hachures are short lines perpendicular to the contour line. They point to lower elevations. Then the distance between the contour lines indicates the steepness of the slope. The greater the distance between two consecutive contours, the less the slope. The opposite is also true. Means the lesser the distance, there will be higher slope. And the contours are always perpendicular to the maximum slope. Different type of lines should be used for contours of major elevations like 100, 50, and 10 foot. Commonly practiced is to identify the major elevations or every fifth line with a border wider line. So if you are showing map, say, so for 100 feet, every change in 100 feet, you will have a different color. You can use those different color, or you just can make a line thicker than the ordinary lines like that. So when I say some contours lines may close within the map, but other will not. For example, I've taken this thing, this 620, 610, these all are contours, but within my map, this 580, though it may be continuous, but for this particular page, it is not closing, right? And say is 570, or it not because of the page, sometimes it doesn't close at all. So when we say contour line may close, may not close. In this case, they will start at a boundary line and at a, so like this. This started 570 started with the boundary line on from the left side, and it stops at the boundary line on the right side. Contours must either close or extend from boundary to boundary. When I say contour lines are parallel, there are two exceptions. They will meet at a glance. So you see 870, 880, they are parallel, but they are meeting at this point. So this is a cliff, right? Vertical cliff. And they will overlap at cave. So normally we say contour line does not intersect, but in case of cave of overhang, they will actually overlap like this. This is a cave, and now these contours 1060 and 1050, they are overlapping each other. So you can see there is some cave over here. When contour line overlap, the lower elevation contour should be dashed for the duration of the overlap. So that's, so see, this is 1040 and 1060. According to this statement, this 1040 should be shown in dash, and the other is shown in the continuous line. So yes, we were discussing a valley. So you see, this is a V shape, right? So as you go from this point, from inside to outside, the elevation is increasing. So this is a valley. Inside is less, outside is high. This type of contours in a V shape shows a valley. So when we say this V point, this point shows a higher elevation. This is the valley. We say U shape. Now this indicates a ridge. As you see, as you go from left to right, it is decreasing. So this is the highest point. So you say this is U point. If the U point shows lower elevation, then it's a ridge. Now again, this is a V shape, and this is a slight rounded shape, or what we call a U shape. So in a V shape, it is a valley, and U shape, it is a ridge. In other words, higher elevation inside, lower elevation outside. This is a ridge, and in lower elevation inside, higher elevation outside, that is a valley. Like this. This is a decreasing depression. So here you can see these are somewhat parallel. So what we call a uniform slope. Here it's not parallel. At this point it's not parallel. It's not equal distance. The distance, if I take this line, for instance, if I don't want to draw a correction over here, draw a line, this distance is not equal to this distance. So this is what we call a non-evenly spaced or non-parallel two lines that has got variable slope. So that's why the slopes here too, the slope may not be numerically equal. Sometimes it's like maybe 2.5%, then 2.75%. But rounding off, it's around 2.75, 2.8, right? But here, this is not the case. You will have a different number altogether. That's what you call, whenever you have unevenly spaced contours, you have a variable slope. So now, how you identify hills and depression is that if your now again you look at those elevations, higher inside, lower outside. You see this line? If I come from left to right, or just look at my arrow. If I start my arrow from this point and I go like this, so we called increasing elevation. This is the contour line representing a hill. Higher level at the inside, lower level outside. This is a hill. Hills may be defined with the positive elevations, and depressions may be defined in negative. Now, what is the converse now? This is what we call a depression. Outer inside, higher values. Mostly, this can be taken as a water body. Water body has a higher elevation at outside, and if we go down, the elevation becomes lower. Then there are Hachures. Hachures are short lines which are perpendicular to the contour lines, used to indicate a hill or slope. So you see, if you look at this better, again, this is a hill, 580, 570, 560, 590. So these are small portion of the hills. So the spacing, if they are very close space, then it means it has a steep slope. That is maybe 2%, 3%, 4%. It is just like a ladder, or what you say, a wooden ladder that you climb. Have a steep slope as against the steps, the ladders, or the steps you provide the building. They are of uniform slope, or what you call the stairs. They are of uniform slope. But if you consider the wooden ladder that people use to mount on it and climb on it, this is what we call a steep slope. Contour space wider apart indicate less below. Contour space close together. Now, if you can compare this contour with this contour, obviously this has got the steeper slope and this has got the higher slope, lower slope. Like this, they are very close together. So this is what we call. And then their contours are perpendicular to the maximum slopes, like this. So different types of lines may be used for major contours elevation. For itself, every 5 lines, they are using a dark brown color. Common practice to identify the major elevations lines, or every 5th line with the bolder on it. So you can see the label on every 5th line. Every 5th line is darker. Another decision that must be made is the interval. The best interval depends on the use of the data. Recommendation is to be elevations evenly divisible by the interval. Large scale, nature of terrain, we say 0.5 feet to 1 feet. Rolling terrain, 1 feet to 2 feet. Hilly terrain, 2 feet to 5 feet. Similarly, in intermediate scale, you can use 1 feet, 2 feet, 5 feet intervals. For small scale, you can use 2 feet, 5 feet contours, 10, 20, or what I mean like this. Just like My contour, first contour will be say 250 feet, the other contours will be 260 feet, the third contour will be 270 feet. That's what I mean interval. But for a large scale, we say 1.5 feet, 2.5 contour, 3 contour, or is what I mean by intervals. Now this ends my lecture 1. I hope I have fully explained you the concepts and uh, all the things that I have explained to you, you have understood. Nevertheless, we have a live session in the on next Tuesday. There we can discuss all your any question that you need to ask, and obviously anything, any ambiguity during my first presentation. Uh, thank you very much, and take good care of yourself.